describing the universe at the absolute tiniest scales. And our sources for this deep dive really highlight the incredible math involved, things like wave functions, state vectors.
Yeah, that math is incredibly powerful.
Yeah.
Beautiful even. It lets us describe a quantum system, but it brings up a really fundamental challenge.
Which is?
How do you actually connect that abstract math description to what you see, to what you measure in an experiment? How does this fuzzy wave function end up meaning a particle hits right here on your detector?
Right. That's the million-dollar question, isn't it? Turning the theory into something, well, real, something testable.
Exactly.
And that bridge, that absolutely essential link, that's what we're diving into today. We're unpacking Born's rule. Our mission, really, is to get a handle on what it is, why it's so critical, like indispensable for quantum mechanics, and what the big implications are. For everything, really.
And Born's rule is that critical piece.
Right.
It's the translator. It takes the abstract quantum state, the wave function or whatever, and tells us how to get the probabilities of different outcomes when we, poke the system, when we measure it.
So it brings probability right into the heart of physics.
Right into the fabric of reality,
Yeah.
which was completely alien to classical physics, that deterministic clockwork universe idea.
Okay, so the core idea, connecting the weird quantum math to the observable world. What is Born's rule like at its heart?
Well, think of the wave function, or the state vector, as holding all the potential outcomes for a system, all the possibilities.
Okay.
Born's rule is essentially the recipe. It tells you how to calculate the chance, the probability of each of those potential outcomes actually happening when you make a measurement.
So it doesn't say the particle is here.
No, not definitively before the measurement. It says, here's the likelihood you'll find it here if you look, or here's the probability you'll measure its spin as up.
And how does it do that? You mentioned something about squaring.
Exactly. The rule connects the probability to a mathematical operation on that description, the wave function or the state vector. Specifically, you take the size or magnitude of the part of the description corresponding to a particular outcome, and you square it.
Squaring the magnitude.
Squaring the magnitude. That number gives you the probability.
So the math holds the potential. Born's rule gives you the odds.
Precisely. And that's why it's just massive. Its significance is huge. It's the main bridge from the theory to experiments.
It's the only way to test the predictions.
Pretty much the only way to get quantitative predictions you can actually compare to lab results. And it introduces this fundamental randomness. It's not just that we don't know enough, like in classical coin flips. The standard view is that nature is probabilistic at this level. Without Born's rule, quantum mechanics would be, well, a mathematical curiosity maybe? Not a predictive science.
Okay, let's dig into that squaring mechanism a bit. The sources mentioned it works slightly differently for continuous things versus discrete things.
That's right. Quantum mechanics deals with properties like position, which can be anywhere along a line that's continuous.
Right.
And properties like electron energy levels in an atom, or spin, which only come in specific, distinct values. Those are discrete.
So how does Born's rule handle continuous position?
Okay, so for position, the particle's state is described by this wave function. Let's call it psi. At any point in space, psi has a value, which can be a complex number.
Okay.
Born's rule says, take the magnitude of that value, psi, at a specific point and square it. So, psi. Now, this number isn't the probability itself. It's the probability density.
Density, meaning like how concentrated the probability is right there.
Exactly. Think of it like population density on a map. It tells you how crowded the probability is at that spot. To get the actual probability of finding the particle in a certain region, say between point A and point B,
You have to add it up over the region.
you sum up that probability density over the entire region you're interested in.
Right, like adding up the population in a whole county from the density map.
Perfect analogy. And a key point is normalization. The total probability of finding the particle somewhere, anywhere in the universe, has to add up to 1.
100%.
Makes sense. Got to find it somewhere. Okay, so for position, square the wave function's magnitude for density, then integrate for probability. What about the discrete properties, like spin up or spin down?
Right. For those, the system state is often a mix, a superposition of the different possible definite outcomes, like our quantum coin being heads and tails simultaneously.
Okay.
Mathematically, we represent this state as a vector, which is essentially a weighted combination of the basis states corresponding to each specific outcome, like a spin-up state vector and a spin-down state vector.
And each part of that mix, each possibility, has a number attached.
Yes, exactly, an amplitude.
Wow.
It tells you how much weight that particular definite outcome has in the overall superposition.
Like how much heads and how much tails is in the mix. Sort of, yeah. And Born's rule then says, if you measure the spin, the probability of getting a specific outcome, say spin-up, is found by taking the amplitude associated with that spin-up possibility.
Let me guess.
Finding its magnitude and squaring it.
Square it again.
Square it again. So amplitude up. That's the probability of measuring up.
So it's the same core idea. Square some number derived from the quantum state description to get the probability of an actual outcome.
That's the unifying theme, squaring the magnitude. Whether it's the wave function value for a continuous probability density or the amplitude coefficient for a discrete probability.
This is where it gets conceptually, well, weird, right? What does it mean that this is how physics works at its base?
It means quantum mechanics is fundamentally probabilistic. That's the big takeaway. Before you measure, the system isn't in one state. It's a superposition of possibilities. Born's rule quantifies the odds for each possibility becoming the reality upon measurement.
And it's not just that we don't know, it's inherent.
In the standard view, the Copenhagen interpretation, yes. These aren't probabilities born from ignorance, like with hidden variables we just can't see. They're seen as objective, inherent features of nature itself.
Wow.
The universe plays dice, essentially.
And measurement is the trigger. The act of looking forces a choice.
It seems to be the case. Measurement causes this collapse of the wave function. The superposition vanishes, and the system snaps into one definite state.
And Born's rule tells you the probability of it snapping into which state.
Exactly. It governs the likelihood of collapsing to outcome A versus outcome B.
Such a radical departure. Let's talk history. Max Born, 1926. How did he arrive at this?
Right, Max Born. He was working with Schrödinger's new wave equation and trying to figure out what the wave function Ci physically was. He looked at scattering particles bouncing off targets. His first thought, apparently, was that psi represented the actual density of the scattered particle cloud, like how spread out the particle itself was.
But that didn't quite work out.
No, it led to contradictions. If it was particle density, the particle should spread out smoothly. But experiments showed particles arriving as distinct hits, point-like detections, not smeared out.
So that interpretation failed.
It did. Which led him, famously, first in a footnote and then more clearly in a follow-up paper, to suggest something revolutionary.
The probability idea.
Yes. He proposed that psi wasn't the density of the particle, but the probability density of finding the single particle at that location upon measurement. The wave function wasn't the particle itself, but a map of where it might be found.
That must have caused quite a stir.
Oh, absolutely. It was a huge break from deterministic physics. Even Schrödinger, who came up with the wave equation, was apparently very uncomfortable with this probabilistic interpretation.
And Einstein's famous quote.
God does not play dice. That was Einstein's reaction, voicing his deep unease with the idea that randomness was fundamental, which Born's rule implied.
Yet, Born's interpretation stuck. It became the standard.
It did. It worked. And he eventually received the Nobel Prize in Physics in 1954, specifically for this contribution, the statistical interpretation of the wave function.
It shows how a seemingly simple rule can just rewrite our understanding of reality.
Absolutely.
So, what are the really big consequences of embedding this probabilistic rule right at the heart of quantum theory?
Well, one of the deepest, most persistent issues is the measurement problem. We touched on it.
Right.
You have the Schrödinger equation describing smooth, deterministic evolution of the wave function when no one's looking. Then, bam, during measurement, you have this sudden probabilistic jump the collapse governed by Born's rule. How do these two processes fit together? Why does measurement trigger this change? The deterministic equation doesn't explain the probabilistic collapse.
It's like two different sets of laws.
In the standard picture, it kind of feels that way. And Born's rule is the law for the measurement part. It dictates the probabilities during that unexplained collapse process.
And you mentioned it kills classical determinism.
Completely dismantles it, yes. In classical physics, give me the position and velocity of everything now, and I'll tell you the entire future.
Right.
Quantum mechanics, with Born's rule, says even if you have the most complete description possible, the wave function, you generally only get probabilities for future outcomes. The future is inherently uncertain.
And it explains weird quantum effects, like interference, that double-slit experiment where particles seem to go through both slits.
Yes, that's a fantastic illustration of Born's rule in action. The wave function associated with the particle actually goes through both slits.
Okay.
To find the probability of the particle hitting a specific spot on the detector screen behind the slits, you don't just calculate the probability from slit 1 and add it to the probability from slit 2.
No, what do you?
You have to add the wave function amplitudes from each slit together first. Combine the possibilities. Then you take the magnitude of that combined amplitude and square it, according to Born's rule.
So you combine first, then square. Cool.
Exactly. Psi1 plus Psi2. If you just added the individual probabilities, C1 plus E2, you just get two overlapping blobs on the screen.
Like throwing paintballs.
Right. But because you square the sum of the amplitudes, Psi1 plus Ac2, when you mathematically expand that square, you get extra terms, the cross terms, the interference terms. Those interference terms are what create the characteristic pattern of bright and dark stripes we actually see in the experiment. It's a direct consequence of adding amplitudes before squaring, as Born's rule dictates.
Okay, that makes sense. Given how fundamental this rule is, but also how it was sort of just proposed because it worked, I can see why physicists would want to derive it from something deeper.
Oh, definitely. That's been a major quest for decades. Is it just an axiom, a postulate we have to accept? Or can we show it logically follows from the other parts of quantum theory or some more fundamental principles?
And have they succeeded? What are the main approaches?
Well, there have been several significant attempts. One huge one is Gleason's theorem back in 1957.
What did that show?
Gleason proved that if you accept the basic mathematical framework states are vectors in a Hilbert space, measurements or projections, things like that, then Born's rule is essentially the only way to consistently assign probabilities to measurement outcomes under some reasonable assumptions, like probability should only depend on the state and the measurement itself.
So if you buy the quantum math structure, Born's rule is almost inevitable.
It shows it's deeply mathematically consistent within that structure, yeah. It's not arbitrary, but it doesn't really explain why nature chose that mathematical structure to begin with.
I see. What else?
Well, different interpretations of quantum mechanics try to derive it in their own ways. The many worlds interpretation folks try to get it from the deterministic evolution by considering infinite universes, or using arguments about rational agents making bets across branches.
That sounds complicated.
It's debated, let's say. Then there's quantum Bayesianism or cubism.
Cubism.
Yeah, they view probabilities as subjective degrees of belief for an agent interacting with the world. They try to argue that Born's rule is the uniquely rational way for an agent to update their beliefs based on quantum measurements.
A rule for rational betting in a quantum world.
Kind of. There are also other approaches like invariance environment-assisted invariance, which uses symmetry arguments involving how a system interacts and becomes entangled with its surroundings.
So lots of different angles trying to justify it.
Yes, and while there isn't one single derivation that satisfies everyone universally, these efforts demonstrate that Born's rule isn't just floating freely. It fits very tightly within the quantum formalism viewed from many perspectives.
Okay. What about challenges or criticisms? Does anyone doubt Born's rule actually works?
No, that's crucial. The challenges aren't about its empirical validity. Born's rule works spectacularly well in predicting experimental results. It's been tested to insane precision.
So the criticisms are more foundational.
Exactly. It's about its interpretation and its status. Is it truly fundamental or emergent? Why does it appear ad hoc historically? Yeah. And as we keep coming back to, its intimate connection to the measurement problem and that uneasy split between deterministic evolution and probabilistic collapse.
And how you interpret the probabilities themselves, objective chance versus subjective belief, changes how you view the rule's meaning.
Right. But again, for actually using quantum mechanics to calculate things we measure in the lab,
it's the bedrock.
Absolutely indispensable, non-negotiable.
You see it everywhere in modern physics, right?
Everywhere quantum mechanics is used. Particle physics, calculating scattering cross-sections, particle decay rates, condensed matter physics, understanding electron behavior in materials, predicting conductivity, explaining superconductivity, quantum optics, describing photon detection probabilities, the nature of laser light, quantum information and computation, predicting the outcome of quantum algorithms, understanding decoherence effects.
Even cosmology.
Even cosmology. Theories about the origin of structure in the universe rely on quantum fluctuations in the very early cosmos, and the probabilities associated with those fluctuations are calculated using, you guessed it, Born's rule.
Wow. So anytime you need a number out of quantum theory to check against an experiment.
You're almost certainly using Born's rule somewhere in that calculation. It's the step that turns the quantum state into a measurable prediction.
Okay, so wrapping up this deep dive, Born's rule really emerges as this absolute cornerstone. It's the vital bridge connecting the strange, abstract math of the quantum realm to the concrete results we see in experiments.
Yeah, and in doing so, it fundamentally injected probability into physics. Max Born's insight back in 26 was revolutionary, Nobel-worthy stuff.
And even though it works perfectly in practice, it leaves us with these deep, nagging questions about the measurement problem, its foundational status.
Exactly. It highlights that tension between the weirdness of quantum mechanics and its unbelievable empirical success.
So it leaves us, and you listening, with a really profound thought to chew on. If nature, at its most fundamental level, really does operate on probability, if God does play dice, what does that truly imply?
What does it mean for cause and effect? For predictability, maybe even for concepts like free will? Is this inherent randomness a limit on our knowledge, or is it the source of possibility in the universe?
Something to ponder until next time.